Okay, so I'm Bill Pfefferman from the University of California, Berkeley, and I'm going to talk about a complete characterization of unitary quantum space. This is joint work with Cedric Lin from the University of Maryland. Okay, let me first tell you our motivation, which is to understand the power of quantum computers with a small number of qubits. Okay, so this is quite a timely motivation. And our results are going to do something reasonably strong. We're going to give two natural problems, so two characterizations. These problems kind of characterize the power of quantum computation with some fixed bound on the number of qubits. Okay, so the first problem we're going to call the precise, succinct Hamiltonian problem. It's a natural generalization of the local Hamiltonian problem. And the second problem is also natural. It's a well-conditioned analog of the matrix inversion problem. Okay, and besides being natural, I think, in their own right, these characterizations have many applications. So first to QMA proof systems and Hamiltonian complexity. This is kind of a field at the intersection of condensed matter physics and computational complexity. And then to classical log space complexity. Okay. So what we're talking about is quantum space complexity, and the primary complexity class we're going to describe is what I call BQ space K of n. It's just bounded error quantum space with K of n qubits. All right, so it's the class of promise problems that can be decided by a bounded error quantum algorithm that acts on K of n qubits. Okay, so more formally, there exists a uniformly generated family of quantum circuits, QX, each of which acts on K of x qubits. So that, if the answer is yes, the probability that we accept after measuring, some output qubit is greater than 2/3. And if the answer is no, the probability we accept is less than 1/3. Okay? So, nothing very strange is going on here, right? We get exactly BQP if instead of being interested in the space, we are interested in the size of these circuits, right? And we bounded it by a polynomial. Okay, so our results show two natural complete problems for BQ space K of n for any fixed K between log and polynomial. Okay, now reductions will use classical K of n space and polynomial time. Okay, there's only one subtlety here that I want to draw attention to, which is that this is unitary quantum space, and what I mean by that is that I'm not going to allow for intermediate measurements in my circuit. Okay, I'm going to just assume that all the measurements are at the end. It's a little bit strange in quantum complexity. We're not used to thinking about intermediate measurements as mattering. That's because we have time-efficient means for deferring them to the end of the computation. The problem is that if you look at the naive way to do this, and the way we always do this, it uses an extra ancilla qubit per each measurement we're trying to defer. Okay, and so by definition, this is not a space-efficient means for doing this. We would gain space. And so it really may be the case that there's kind of two quantum space classes. One unitary, where there's no measurements in between, and one where there are measurements. Okay, and these actually could be different things. Okay? Great. So now, somewhat strangely, our initial motivation wasn't about space. It was about quantum Merlin-Arthur and kind of settling some foundational questions regarding quantum Merlin-Arthur, or QMA. These are the problems whose solutions can be verified quantumly given a quantum state as a witness. So here's Arthur, and you can see he's super happy and he has stars floating around. That's because he has a quantum computer. And he's receiving, a quantum state from Merlin to convince him of the validity of some mathematical claim. Right, so QMA with completeness C, soundness S is the class of promise problems L, so that if the answer is yes, there exists a witness that Merlin can send to convince Arthur to accept with probability greater than C, whereas if the answer is no, then whatever Merlin sends, he's going to reject with high probability. Okay, so if I say QMA without any further parameterization, I'm talking about bounded error QMA, and we know from amplification results, you get the same class as long as the completeness-soundness gap is bounded by an inverse poly. It's kind of what you'd expect. Okay, so to motivate QMA, we have this physically relevant natural problem, which is called the K-local Hamiltonian problem. The input is a K-local Hamiltonian. It's just a 2 to the n by 2 to the n Hermitian matrix with this specific form, which we call locality. It just means it can be written as the sum of K local terms. So each term, hi, just acts non-trivially on at most K qubits and has the identity on the rest of the space. Okay, so it's this big Hermitian matrix with this property, and we're promised either that the minimum eigenvalue is less than A or greater than B, okay, where this gap, B minus A, is bounded by an inverse polynomial in the number of qubits n, and we want to know which is the case. Okay, natural problem. And for the sake of this talk, we're going to be interested in two generalizations of QMA, especially the first one. I call it precise QMA. It's the same class with an inverse exponential gap, okay, of completeness and soundness. And then K-bounded QMAM, we'll use this for our proofs. It's just the kind of intermediate class where Arthur's verification circuit acts on K qubits, and Merlin sends an M qubit quantum witness. So standard QMA would just be, K and M would be arbitrary polynomials. Okay. All right, let's talk about the first characterization, which will be our focus. I'll call it the precise succinct Hamiltonian problem. So let me tell you about this problem. First, let me define a natural thing, which I'll call a succinct encoding. So we say a classical Turing machine M is a succinct encoding for a 2 to the k of n by 2 to the k of n matrix A if effectively on input a row index, which is just a number between 1 and 2 to the k, this machine spits out the non-zero elements in the ith row of A. Okay? Using so efficient resources like polynomial time and k of n space. Okay, so this, of course, it's not the case that every matrix will have one of these encodings. In general, it will imply like a sparsity condition, for example. Right? Okay, now here's the problem. We're given as input this succinct encoding of this giant matrix, 2 to the k of n by 2 to the k of n, Hermitian positive semi-definite matrix A, and we're promised either the minimum eigenvalue is less than A or greater than B, okay, where this gap is bounded by an inverse exponential quantity in K. Okay, now wait a second. We just saw a very similar problem, right, which I called the local Hamiltonian problem. There's two main differences here. Okay? First, the input is succinctly encoded instead of local. Okay? It's a strict generalization of what I mean by local. And two, the precision needed to determine the promise is inverse exponential in K instead of inverse polynomial as it was in the prior slide. Okay, great. And our result is that this K of n precise succinct Hamiltonian problem is in fact complete for this BQ space K of n class for any K between log and polynomial. Okay, great. So let me sketch the proof. The upper bound is the more interesting direction, and I'll divide the sketch into two parts. In the first part, I'll show that this K of n precise succinct Hamiltonian problem is in the variant of precise QMA, in which Arthur's space and Merlin's proof are both bounded by K of n qubits. Okay? Let's just recall what the problem was. I just said it. We're given as input the succinct encoding of this 2 to the k of n by 2 to the k of n matrix, and we want to estimate the minimum eigenvalue of the matrix to within inverse exponential precision. Okay? So now, here's the protocol. Arthur's going to ask Merlin to send the eigenstate psi that corresponds to the minimum eigenvalue. Okay? Just the eigenvector that corresponds to the minimum eigenvalue. And Arthur's going to run phase estimation with one ancilla qubit on the unitary e to the minus ia. So if you're not a quantum person, A is a Hermitian matrix, so this matrix exponential e to the minus ia is a unitary, which we're going to assume for the moment we can implement exactly. We'll talk about that in a moment, why that's justified. So we're going to run this on this unitary and Merlin's state that he sends you, psi. Okay, so here's the state. So an extremely simple quantum circuit with one ancilla qubit here. And Arthur's simply going to measure the ancilla qubit and accept if he sees 0. Okay? And because this is phase estimation with one ancilla qubit, it's easy to see that we get the 0 outcome with probability that's just slightly higher, okay, if the minimum eigenvalue is less than A than if it's greater than B. Okay? But this is, of course, exactly what's needed to establish the claimed bound. It's what it means to be in precise QMA, that we accept with slightly higher probability in the yes case than in the no case. Okay? So the remaining question that's interesting here is, how do we implement this unitary? Because remember, we're not given e to the minus ia as a unitary, as the input of the problem. We're given a Hermitian matrix that's described by a Turing machine. Okay? So how do we take that and implement this unitary? And furthermore, we need to implement it with incredibly high precision, with precision 2 to the minus k, since otherwise the error in the simulation would overwhelm the gap. In other words, the whole reason we're executing this protocol in the first place is because of this inverse exponentially small gap we're getting. And if the error in implementing this unitary, e to the minus ia, is going to overwhelm that, there's no reason to do this at all. Okay? But luckily, we can invoke recent so-called precise Hamiltonian simulation results of Andrew Childs and collaborators from only around 3 or 4 years ago to do exactly this. So what they do is literally they'll be given the succinct encoding of this Hermitian matrix, and they'll implement this unitary e to the minus IA within precision epsilon in space that scales with log of 1 over epsilon. So this is precisely what we want, because we want to implement this unitary to within precision 2 to the minus k. We want to make the space bounded by k. Okay, great. So in the second part of the upper bound, we'll show that the class we just put this problem in is in BQ space k of n. So together with the last slide is we'll establish our bound. Okay, so the first step is we're going to error amplify the precise QMA protocol. Our goal is to obtain a protocol with inverse exponentially bounded error in the witness length k. So we have an inverse exponential gap, and we want to make inverse exponential bounded error. Okay, like completeness 1 minus 2 to the k and soundness 2 to the minus k. Okay, now of course we know how to do this, right? You could just repeat the protocol and take a majority vote. That's the naive way of amplifying a QMA protocol. The problem is that doesn't preserve the verifier's space, and we don't want to change it. We want to keep it at k of n so that we can put everything in BQ space k of n at the end of the day. Okay, and this takes some tricks as kind of one of the technical parts of the work. We actually developed some of the first space-preserving QMA amplification procedures. Okay, procedures which you can amplify to within inverse exponentially small bounded error without changing your space, the space of the verifier. Okay, so now what we're going to do is take this verified protocol, and this is my favorite part. We're going to just guess the witness. Okay, we don't want a witness because BQ space k of n does not have a witness. And to do that, we're going to just guess it. So what do I mean by that? We're going to consider this amplified protocol run on a maximally mixed state on k of n qubits. So if you don't like quantum, you don't like maximally mixed, you can just think about the new amplified protocol run on a randomly chosen computational basis state. So here's the point. Our success probability is going to drop, obviously, right? Because Merlin's not giving us the state. We're just running a random state, right? But it's going to drop in a way so that the completeness is still a little bit bigger than the soundness, right? And that's precisely what we want. So this new no-witness protocol has a precise gap. And of course, now we're going to amplify again and use these same space-efficient QMA error amplification techniques that we develop in the paper. Okay? It's going to get an exponential time, but we don't care. We're going to get k of n space, which is the claimed bound. I will say a little bit about the hardness, not much, which is that this same space-efficient amplification techniques that we developed for QMA is actually also going to be used to show that this problem is hard for BQ space k of n. Okay? And then the rest follows from Kitayev's result that the local Hamiltonian is complete for QMA. Okay? Okay, great. So that's the sketch of the proof. The main application of this is a very natural statement, I think, which is that precise QMA is exactly equal to p-space. We give an upper bound and a lower bound, okay, which were not known before. So the question, of course, we're asking, how does the power of QMA scale with the completeness-soundness gap, right? So let's just recall, precise QMA is the variant of QMA in which the completeness minus the soundness is bounded by an inverse exponential quantity. Where the standard QMA would be inverse polynomial. Right, so I won't explain the proof, and the reason is because I actually just showed it to you in a slightly different language. So I'll just take my word for it. Both upper and lower bounds of p-space follow from our completeness result that I just showed you, together with an old fact of Watrous, which is that BQ p-space is equal to p-space. BQ p-space is just BQ space with an arbitrary polynomial space bound. Okay. All right, good. So let me, in the next few minutes, let me just briefly sketch this other characterization. I'm not going to prove things, but I'll talk a little bit about it, which is this well-conditioned matrix inversion problem. Okay? Let me talk just very briefly about a subject that I hope is somewhat familiar to complexity theorists, just the classical complexity of matrix inversion in one slide. So what do I mean by the problem? I simply mean that I'm given a non-singular, just a fancy word for invertible, n by n matrix, A with integer entries, and we're promised that either a single fixed element of the inverse is like sufficiently large or sufficiently small. Okay? These are, of course, arbitrary bounds, these 2/3, 1/3, and you don't have to make it a decision problem. I just thought it was easier that way. Yeah, so this is the matrix inversion problem. And something we've known from an older algorithm than I am is that this problem can be solved in log squared of n space. Okay, and the thing I want to capitalize on is not believed to be solvable in log n space. It's kind of a little bit strange if you haven't seen this before. Okay. In fact, if it is, then L is equal to NL, and L is equal to det, and this is kind of a whole bunch of spaces, log space classes kind of collapse. It's kind of the log space equivalent of P equal NP. So there really is this kind of gap here. So the question, of course, we're going to be asking is, can we do better quantumly? After no progress on this for a long time, Tashma in 2012 gave a partial answer to this. He said that he showed that if you have a well-conditioned matrix, okay, then in fact you can solve this problem in quantum log space. Okay, but let's be a little bit careful. First of all, remember we were talking about unitary versus non-unitary quantum log space. He was talking about the non-unitary class, where you actually have intermediate measurements. Okay, and remember this might actually be a sharp distinction, right? A distinction that matters. Okay, so Tashma shows that the well-conditioned case in which we have the same problem with a polynomial upper bound on the condition number kappa. A condition number is just the ratio of maximum to minimum singular values. It's a well-known proxy for the invertibility of a matrix, right? He shows that this problem can be solved in non-unitary BQ space log n. And so this, of course, appears to attain a quadratic speedup in space usage over classical algorithms. But I say appears because we don't know how this well-conditioned restriction affects the classical complexity. Right, so it kind of begs the question, how important is this well-conditioned restriction? So for example, could we also solve the general matrix inversion problem in quantum space log n? And I see our results now as kind of being like a negative answer to that, okay, in the following sense. We're going to show that well-conditioned matrix inversion is in fact complete for the unitary class with log n quantum space, okay? So we improve Tashma's result in two ways. The first way is to get rid of these intermediate measurements. So we're going to give a new algorithm, and we're going to show it's going to be unitary. Okay, it's not going to use the intermediate measurements that Tashma used. Okay, but then the second part, which is I think the motivation for the first part, because you can always ask, well, who cares about intermediate measurements? Well, we can actually show this is hard for this class. Okay, the well-conditioned matrix inversion problem is actually BQ space log n complete. Okay. And I think what this suggests is that probably the well-conditioned constraint that Tashma was finding in his algorithm is likely necessary for quantum log space algorithms. Okay? Unless somehow the well-conditioned constraint does nothing to the complexity of the problem, which I think is unlikely. Okay, let me just say very quickly that we can generalize everything I just said from log n qubits to characterizing k of n qubits if you just reparameterize the problem, kind of as we did before. So we have this result that says, for any k between log and polynomial, the k of n well-conditioned matrix inversion problem is complete for BQ space k of n. So the input now is just a succinct encoding of a 2 to the k by 2 to the k positive semi-definite matrix A with an upper bound on the condition number of 2 to the k of n. And now we're just asked, again, the same problem. Okay, a fixed element of the inverse, either sufficiently large or sufficiently small, and which one is it? Okay. Let me conclude with some open problems. So first, I think this is the one that I'm most interested in. Can we use our precise QMA equal p-space characterization to give a p-space upper bound for other complexity classes? So I think the complexity class that most needs a p-space upper bound right now is QMA2. It's QMA with two unentangled provers. I kind of won't get into it, but there's this whole beautiful area talking about QMA2 and the power of various two-proof protocols and quantum proof complexity, or quantum Merlin-Arthur games. I think it would be great to show QMA2 is in precise QMA, which would then show that QMA2 is in p-space by our results. How powerful is precise QIP? So if you have interaction between the prover and the verifier. The best result I'm aware of, by the way, is that precise QIP, which means you have a doubly exponentially small gap, is equal to exp. That's an old result of Watrous and collaborators. But as far as I can tell, we don't know where this precise QIP sits between p-space and exp. And then I think that we're leaving this gap open, which is to say something more about non-unitary quantum space. Are there any kind of natural complete problems for that class, and is that class equal to the unitary class? I think we leave that wide open. All right, thanks. Yeah, it's probably something that you can't capture classically. I think that's true. Yeah. Yeah. Yeah.
I noticed in your definition of quantum space,
Yeah.
the quantum circuit could depend on the actual input rather than the input's length.
That's right.
So how important is that formulation? Is there a way of defining quantum based on computation that's more similar to classical where you're read-only access?
Yeah. Absolutely. Yeah, you can do almost the same thing. We have an appendix in our paper, which I'll just point you to, which says, like equivalent formulations of quantum log space, and one of them is like a kind of a quantum Turing machine type definition, which I think is precisely what you're asking about. It's just a little hard to define quantum Turing machine in a model that's kind of, natural for a short talk. So that was the reason I chose the kind of a uniformly generated circuit model. But absolutely, you can definitely talk about it in other ways.